Hello everyone, welcome to my video. This is example 3/67 in lecture 11. As always, please make sure you read the question first. We have a small object is placed on the inner surface of the conical dish at the radius shown, which is right here. If the coefficient of static friction between the object and the conical surface is 0.3, for what range of angular velocities omega about the vertical axis will the block remain on dish without slipping? Assume that speed changes are made slowly so that any angular acceleration may be neglected. Okay, so nicely we have already our angular acceleration is 0. So when considering the question like this, you always want to set up the physical model first. Okay, how does physics works in this case? When we are talking about slipping, which is this object little, what is called this m here, how does it slip when it rotates? Where does m go? That's my question. Ask yourself. I hope you can realize m can slip this way. Okay? When it's too fast, when this cone is spinning too fast, m will apparently get out. However, is this the only way that m will go? It's not. What about when the cone is stopped? Or when the cone is at a smaller speed? Well, if this angular speed is not enough, can we have our m sliding down instead of going up when the cone is not spinning fast enough, right? Or when the cone is stopped, right? When the cone is stopped, of course, m will slide down. So when we are talking about spinning, we have two scenarios to think about. It's going to slip up, I'll use a different color, and it will also possible going to slip down. Right? You have two scenarios to consider. Okay. With that in mind, you can think about how do you draw the free body diagram. And apparently, slipping up and slipping down, the free body diagram will be different. Therefore, for slipping up, your free body diagram will treat this little m as a particle. I can simplify that. The GNEF method, gravity is the first. You always have gravity. N is supporting force or the normal force. Will always coming from the surface. Goes this way. Right? On our diagram, it will be like this. We have Fn. And also, do we have any external force in this case? No external force. Then jumps to our fourth step, the friction. Where does friction go? Well, friction will be different depending on where do you go. To prevent the block from slip up, the friction will go against it. So when it's a slip up situation, your friction will be going down, and that is perpendicular to normal force. All right? So this is spinning. So how do we analyze this? When it's spinning, and in this case, there's no theta, no r given, right? When spinning, if there's no r or no theta given, so our theta system is, we're going to rule out in our pool already. So either xy system or the nt system. And in a spinning or in a circular motion scenario, the nt system is the one that you should want. Now, the nt system, if you recall the car on the track example we did in class, where do we set up the nt system in this case? Remember, t should be tangential to the motion. right? And n will be perpendicular to that. Now, in this case, where does the block go? Like, just looking at what you have right now. The block at this instant is going into the page, right? So the block, this is motion, into the page. Okay, so that is your tangential. This is your tangential. Going into the page is your tangential direction. Then where is your n direction? Your n direction, number one, is always perpendicular to the t direction. Number two is always pointing to the center. So this block is making circles with respect to this axis, right? It told you in the question. So our n direction would be this way. Right? This is our n positive direction, and while your t positive direction would be going into the page. Right? But we don't need the t direction. Like so. Okay? Understanding that part, this is your n positive direction. Okay, now, looking at these three forces, what you want to do is to break up them into the n direction and the vertical direction. Right? Vertical direction, there's no movement on the vertical direction as we did for the car example in class. So the vertical direction force will be balanced, and then this force, this resultant force towards the center, would give you the normal acceleration that is changing your velocity's direction. Okay? Given that, our Fn can be broken into Fn cos 30 degrees and Fn sine 30 degrees. And for your friction, can also be broken into, you have a friction. This will be F sine 30 degrees, your friction. And also, I'm making my drawing too small, so make your drawing large so you can write it clearly. Well, because I'm on iPad, I can zoom in, but in the exam, when you're handwriting, make sure you make it large. I'll give you plenty of space. So you'll have a F cos 30 degrees. Okay, this is a slip up situation. Okay, for the slip down scenario, how would you redraw your free body diagram? Okay, feel free to pause here and give yourself a try. For slip down scenario, we'll still have our gravity, G, N, E, F. Gravity is still there. Normal supporting force is still there coming from the surface. But when I'm sliding down, my friction is going against my motion, which would be pointing up the ramp or inside the cone. So this is my friction. Okay, still, my n direction, n positive direction is pointing towards the axis, right? My n positive direction. So I need to break Fn and friction F into the n direction and the vertical direction. We can call it y direction. Okay, we'll do this again. Your friction would be broken into these two guys. This is F cos 30 degrees, and you have your F sine 30 degrees. Okay, and for your Fn, you would have, I want a straight line. Okay, feel free to use a different color just to remind yourself there are two forces. This is Fn sine 30 degrees, and this is your, I'm really running out of space here, so I just use smaller font. this is your Fn cos 30 degrees. Where is your 30 degrees? This is the 30 degree. Okay, and in this case, this is your 30 degree. Okay, you should be able to find that from the diagram, from the geometry over here. Okay, this is a 30, so when you draw this, this will be a 30. Okay, that's our free body diagram. Because we want to find the velocity or the angular velocity, angular velocity in a circular motion is related to your angular acceleration. The normal acceleration. Right? Your angular acceleration is 0 already. Okay. Your acceleration. Okay, we have acceleration. We have m, and then Newton's second law, the force. That's why we did the free body diagram. So therefore, I will do the slip up scenario here, but I'll give you the answer for the slip down scenario, but you need to calculate the slip down scenario for yourself. Slip up, when the block is going to slip up, okay, or just before it's going to slip up, you have sum of Fy equal to 0. Again, just to remind myself, this is my y positive direction. Sum of y equals 0, and also sum of Fn equals to man. Normal acceleration. Okay? Now, I'm looking at the slip up scenario. So I have, on the vertical direction, I have Fn cos 30 degrees equals to friction sine 30 plus mg. And for the n direction, I have Fn sine 30 degrees plus F cos 30 degrees equals to mr omega square. Okay, An is equal to v squared over rho, or r omega square. Well, this is equivalent to r. Okay, why I'm not choosing this v squared over radius expression over the r omega square, the reason for that is because I'm given the angular, or I'm being asked to get the angular velocity. Okay, you can get the tangential velocity, that's fine, but you're being asked for angular velocity omega. Okay, so that's why I'm using the r omega square here versus v square over r. Okay, and also we need to remember you have friction. Friction is always mu Fn. Right? Friction is coming from the supporting force, the normal force. All right, given that, we'll go simplify. We'll simplify this. For the first equation, this guy, we're simplifying to Fn cos 30 degrees minus mu Fn, we're subbing the friction here, sine 30 degrees equals to mg. And for the second equation here, we are simplifying this into the normal force Fn sine 30 degrees plus mu Fn cos 30 degrees equals to mr omega square. And remember, omega is the parameter that we want. Okay, so you can actually find out if you isolate Fn for each equation and make them equal to each other, this Fn will be gone. And everything, you will be ending up with the mu and the angle 30 degrees. M will also be gone as well. Okay, give it a try by yourself. I'm just now giving you the answer here. Eventually, you should get something like this. Cos 30 degrees minus mu sine 30 degrees over sine 30 degrees plus mu cos 30 degrees equals to, on the right hand side, g over r omega squared. Fn is gone, right? This is simply by making a huge fraction on left hand side and right hand side. On left hand side, all these are gone. On right hand, m is cancelled out. Okay, this is your expression here. So you can find out your omega is actually only related to the angle, to the friction coefficient, and the radius. Therefore, for the slip up scenario that we're working on, your omega equals to 7.21 radius per second, and this is actually your omega max. Okay, as long as you are not spinning over 7.21 radius per second, that block won't slip up, will remain there. However, we also discovered another scenario. If the velocity is too slow, then it's almost like a still situation. The block will start to slide down. So you can try that by yourself using this free body diagram. Okay, rework on those equations. Do it by yourself. I'll give you the answer here. So this is slip up. Okay, this is our answer for the slip up scenario. And slip down. For the slip down scenario, your omega minimum can be calculated as 3.41 radius per second. From the physics perspective, that means if you the cone is spinning less than 3.41 radius per second, the block is going to slide down. Okay, that's it. Thank you for watching. I'll see you next time.